So I'm gonna start out. I basically have an outline here of things that I would like to be prepared for. Now, in addition to this, we might be interested in some of the conditions that are necessary for performing a t-test or calculating a confidence interval and so on and so forth. Some of the assumptions that you would make when you do that about whether a sample is normal, whether a population is normally distributed, and so on and so forth. We started to hear a little bit about that in doing two sample t-tests or in the t-distribution. Some of the assumptions are a little bit different than for the z-test, z-scores, or for the central limit theorem when we know what the standard deviation of the population is, or when we're dealing with a very large sample, somewhat slightly different assumptions. So a lot of that is in the PowerPoints. So I think that's something that you could probably just, grab out of there, look up, or just find even just search in the textbook and find. So I'm not too worried about you guys tracking those down. Okay, but I want to make sure that we understand how we approach these problems. As we continue forward, we're going to be getting into more complicated statistical analyses, but this idea of the confidence interval and the single sample t-test is kind of one of the foundations for this whole thing. And it's a little bit easier to understand than directly impacting, the two sample t-test or analysis of variance as we move on, and so on and so forth. I think chi-squares you're going to find pretty simple, but the t-test and analysis of variance could be a little bit complicated for you when you look at the formulas, but they're pretty simple concepts and when we really get down to it. So I want to go through how we make decisions here, kind of how we build our flow chart of decisions that we make from the top to the bottom. So one of the things that we're interested in doing is calculating a confidence interval. One of the things you might want to consider is, why did we want a confidence interval? We want a confidence interval because we want to know more about a population. For instance, we specifically want to know where the middle of the population is, where the mean is, and we can't sample the entire population. We can't get the data for the entire population, but we can take a random sample from that population. The larger the sample is, the more confidence that we have in the result of that sample when we are estimating the mean. But we really would like to be able to quantify how much confidence that we really have in the result of that sample, because then we can make judgments as to whether the mean for one population is the same as the mean for a different population, or if when we measure these two populations, if the means are different only because just random chance we happen to get a few people that were lower numbers in this sample for this group, and we got higher numbers in this sample for this group, and the difference is really not a difference in the true mean for the two populations. So confidence interval is important to us because it gives us a better way to judge how accurately we really know what the mean is when we take a sample. Okay, so there's a few situations we can get into when we calculate a confidence interval. First of all, you would only do a confidence interval for sample, right? If you knew the mean of the population, you wouldn't need a confidence interval. You know what it is exactly, so there's no need to know a range of anything. The confidence interval is a situation where you are estimating the mean based on a sample that you took, and you want to know how much can I rely on that to represent the true mean of this population. Okay, so there's a few situations we might find ourselves in. The best situation of all, if we know what the actual standard deviation of the population is. Very rare situation, not going to happen very much, but it's kind of a kind of thing where when we're practicing or when we're testing the central limit theorem and we want to understand the central limit theorem, we might have some examples where that might actually, where we might get a problem where we're given that number, or where that might actually take place. The other situation is where we don't know sigma, but the sample size is quite large. Okay, 100 people, 200 people, 1,000 people. We actually do come across a lot of studies where the sample sizes are very large. Okay, in that situation, for our purposes, we may say to ourselves, well, we're going to say, even though we don't know what sigma is, because the sample size is large, we're going to allow the standard deviation of the sample is equal to, approximately equal to, the standard deviation of the population. So we're going to make believe that we know it. We don't really know it. And we are introducing an extra error when we make that assumption. It's not like there's no cost to that assumption. But for our purposes, we're willing to take that risk. The other situation is when we take a sample, we don't know the standard deviation of the population, and the sample is small. For our purposes, most of the time, we define small as 30 or fewer sample points or people or measurements and so on and so forth. In that case, we can't reliably say that we know what the standard deviation of the population is. So in that case, we use the standard deviation of the sample, right? But we increase the spread for a confidence interval. We increase the spread of our confidence interval. And the way that we increase the spread of our confidence interval for that extra, to account for that extra uncertainty, because we don't know the true population standard deviation, is that we employ the t-test instead of the z-test, the t-distribution instead of the z distribution. And the t-distribution, it looks very much like bell shape that we get with the normal distribution, but it's more spread out. And in fact, there's a different t-distribution for every sample size. So as you go down from 29, sample size of 29, the t-distribution is more spread out. As you go to 20, sample size of 20, it's more spread out, even more spread out. And a sample size of 5, it's very spread out. Well, what does that do? That means that the distance that we have to go in standard errors to catch 95% of the possible sample means that we would get for a certain sample size, instead of that being 2 standard deviations to the right and to the left of the mean that we calculate from our sample, or 1.96 as we general, if we're going to be a little more accurate. But now it's going to be more than that number. And it's really going to depend on the sample size. How much more than that number? In the case of, I think, when we took the sample size of approximately 25, which was 24 degrees of freedom, we decided that instead of being 1.96 standard deviations to the left and the right of the mean, the confidence interval had to be 2.06 standard errors or standard deviations of the means to the left and to the right of the mean that we calculated, right? So we use the t-distributions. Okay, now the problem with that is that we don't have a book that has a different t-distribution for sample size 11, 12, 13, 14, 15, 16, like we have a single z. We don't have a t table like we have the z table for every one of these different sample sizes. So what we have instead is a single table that will give us, for any sample size, basically, it'll give us what that t-value has to be in order for us to be able to estimate that we've captured 95% of the possible sample means that we would get when we take a sample from a population of that particular size. So really, what we're interested in is that list of 95% confidence intervals, t-values for 95% confidence interval for each different sample size, so we can employ that. Okay, a little less convenient than using the z-table, which gives us an actual probability. It gives us a very firm window of 1.96 standard deviations left and right. And then when we actually employ it later on to do a t-test, gives us an actual number for the probability of getting that extreme a sample when we're comparing it to something else. Okay, instead of just being able to say yes or no like we do with the t-test, as far as rejecting the null hypothesis. But we'll get on to that and it'll make more sense to you. There's another situation we might find ourselves into that we really didn't get a chance to talk about much last night. And that's the idea of proportions. Okay, we looked at the idea of having a binomial distribution, which looks pretty much like a normal distribution, very similar to normal distribution. And we were in a situation where we were interested in establishing a confidence interval for that proportion. Okay, where might you do something like that? Well, for instance, if we're sampling a population and we want to know what the prevalence of HIV is in that population, and we sample that population, and we come up with a number of 150 people out of 1,000, so we think maybe the prevalence is 15%, right? Well, we only sampled 1,000 people. We didn't sample the entire population. So we need to know how confident we are, what the true range is, that we can be 95% sure that we actually know what the proportion in that population is. In other words, we in our sample it was 150 out of 1,000 or 0.15. However, if we use a confidence interval, then we can go a little bit further and say, well, we're 95% sure it's really between 0.12 and 0.18 or something like that. Okay, or we're 95% sure it's between 0.1 and 0.2. So we have a better understanding of where the true proportion might be, not just a guess at what it might be with a single number without having any idea how accurate that number might be. So we have proportions as well. Anybody want to guess as to whether we use the z-score or the t-score for proportions? One of the rules, one of the assumptions that we talk about that we made in the PowerPoints about calculating, we use the z-score. Anybody know why? Excellent, Lucia. Anybody know why we use the z-score instead of using the t-distribution? Okay, remember we had a rule about proportions? The rule about proportions was that each side of the proportion has to have n equal to, anybody remember what it was? Has to be equal, n is equal to 15, right? So in other words, if I told you that's each side. So in other words, if I told you that we took 100 people, took a sample of 100 people, and we found for those 100 people that 10%. I'll get to you in a second. I'll get to that question in a second. Okay, for 100 people, that we found 10 that had the disease, 10 out of 100. Okay. So the proportion is equal to the prevalence. I'll call that p cap. For our sample proportion is equal to 0.10. Okay, that's p cap. Can I calculate, given the assumptions that I have to make, particularly about each side of the proportion having a sample size of 10, can I calculate a confidence interval and be consistent with those rules now? What do you think? Is that a yes or no? Can I calculate a confidence interval for this sample? Right? No, I can't, right? Because each size has to have a sample size of 10. So in other words, in this case, the one side had, in other words, we have 10 people that had the disease, had diabetes, let's say, and we had 90 people that didn't have the diabetes. So the side that doesn't have diabetes, that satisfies that requirement for our proportion. But the side that does have diabetes only has 10 people, so it doesn't satisfy our rule about having each side of that proportion being equal to 15. Okay, I'm going to take the same situation, except this time I'm going to look at a situation where the p cap is equal to 50%, right? Except this time my sample size, my total sample size, is equal to 40 people, right? Sample size over here was 100 people. Sample size over here total is only 40 people. Can I calculate a p cap for this, a confidence interval for this proportion of this condition in this other population? Do I have 15 people in each side of the proportion, the yeses and the nos? Yeah, I do, don't I? Because I have, since it's 50%, I have 20 yeses and 20 nos, right? So if my minimum sample size for doing a proportion is 15 on each side, well, I always have at least 15 people plus 15 people. I always have a sample size of at least 30 people. So I can justify using the Z distribution. And if I don't have 15, well, we're kind of violating our assumptions on doing the confidence interval for proportions. It's going to be too small a sample size to do it accurately. So is everybody comfortable with that? That's the reasoning behind, using that Z-score. It's kind of a little bit of a twisted reasoning. If you're a real, professional, high-end statistician, it's kind of like a little kind of simplified, but that's kind of the logic behind it. Okay, when we deal with proportions, we don't consider the t-test because we're only going to do it when we have a sample size of at least 30, including 15 in each part of the proportion. Okay, now once we get through the confidence interval, our next application for the same principles is going to be our single sample t-test. Now, our single sample t-test, when do we employ something like that? Well, when we have two populations, right? If we're only looking at one population, we just want to know roughly where the mean is or have an impression of where the mean is, we do a confidence interval. It just deals with that sample. When we start to get into the t-test, we're starting to compare the means for two different populations. Okay, as it happens in the single sample t-test, the population mean, whoops, we got it, population mean for one of the populations is known. The population mean for the other one isn't known, so we have to take a sample. So this is a situation where we're going to calculate basically kind of a confidence interval and see whether or not that other number, that known mean for the other population, is likely to be similar to what our population means are likely to be. So it's almost like taking a confidence interval and seeing whether or not the other numbers included within that range, so that if it's included within that range, you might be tempted to say, I can't really tell if they're different because my true mean and my sample population could be that value that we're comparing it to. But if it's outside that 95% confidence interval, we're saying that it's so far away from our sample mean that it's not likely, or it's less than 5% chance that our true population mean for our sampled group is the same as for the other group where we know the mean. Okay, so that's kind of what we're doing there. We kind of want to use this idea of a certain number of standard errors apart or standard deviations of means apart to be able to say that these two groups could have the same population mean, or different population mean. So we got the same situation here. If sigma is known, if the standard deviation for the population of the sample that we're testing is known, we can use the z-score. And we can use 1.96 as the level at which we're going to say that they're far enough apart that we can say that they're two different means for these two populations. And if sigma is not known, if population standard deviation is not known, but the sample is large, again, we can make the assumption that our standard deviation for the sample approximates the standard deviation for the population, so we can use that in place of sigma. And then finally, if sigma is not known and the sample is small, well, then they're forced again to go to the t-score in order to solve this. And proportions? Well, proportions, we stick with the z-score anyway. So I'm going to go run through some samples here so that we can see how this is going to act, or how this is going to work in real life. So some of these I'm going to do by hand, and some of these we're going to do using SPSS. Okay, before I go any further, questions. Do we have any questions on this so far? Okay. Yes, yeah, 15 on both sides. Anybody have any pressing questions at this moment? Okay, so I'm going to go ahead and I'm going to do a couple of examples. And I'm going to start with the, I'm going to take, well, tell you what, we kind of went through these samples before. I didn't go through a proportion. Okay, I'm going to start, let me just go back here and see what I have on this. I was going to go use these again, but okay. Okay, let's take a look at this. I'm going to look at this first from the perspective of the confidence interval. Mean SAT score for a population of first-year students at Hunter is 620. The standard deviation of scores in this population is 95. So we know sigma in this case, don't we? Right? If you got this problem, first thing you would notice, we know sigma. The standard deviation of scores in the population is 95. Okay, the mean SAT score for the population is 620. So we know both the mean and the standard deviation for this population. An investigator believes that the mean SAT score for the first year psychology majors is different than the mean score from the population. Okay, we did a similar example to this before. The mean of a sample of 36 randomly selected first year psych majors is 648. So let's see. We know that the mean of a sample size of 36 is 648. So I'm gonna just focus on that part right there. And I'm gonna say to myself, let's find our confidence interval for the population of first year psychology students that wound up with an average score of 648. So let's calculate our 95% confidence interval. Okay, and let's see how we would approach this. Okay, so first thing I'm going to say to myself is, do I know sigma? Do I know sigma here for the sample? Anyone want to hazard a guess? Do I know sigma at this stage? I know sigma for the population of first year students at Hunter. I don't really know sigma for the population of first year psychology students, right? So I would say I don't know sigma for this particular situation. Okay, however, I could, if the problem gave you license, for instance, we might say in this problem, assume the two groups have the same standard deviation. The two populations have the same standard deviation. If someone said that to you, then you could say, yes, I know sigma, right? Okay. However, if that's not there, then you might not be able to assume that they both have that the group A, which is student non-psychology students, has the same standard deviation as the scores for psychology majors, right? So you may not be able to, in that case, you may not be able to say yes, no. However, we do have a large sample size, right? So if that statement was there, or if we have a large sample size, 36, more than 30, then we're going to act as if we can use the z-score. Either one of those two situations would have met our criteria before that allows us to use the z-score. Okay, everybody comfortable with that? My reasoning there? If they told me what the standard deviation of the population was, for the population that I'm taking the sample from, that is, if they told me that I could assume it was a certain amount, like in other words, assume that it's the same as this other population where we measured the whole population and we know the standard deviation, then I can use the z-score. But in this case, I have a sample size of 36, so I can't. So I can use the z-score anyway. Okay, so now we have a sample size of 36. So on and so forth. Now, we need to know what the standard deviation of that sample is, right? Well, in this particular case, they didn't give us anything. So we have no choice but to assume that it's the same standard deviation as the population is. Okay, let's say, for instance, that instead I told you that the standard deviation for the sample is, I'm going to make up a number here. Let's see, I want this to work out pretty well. I'm going to say that the standard deviation for the sample, I'm going to call it 50. Okay? Well, maybe not 50. Let's call it 60. Okay, you get to see why I'm saying that. Standard deviation for the sample is 60. Okay, so it's different, it happens to be different than standard deviation for the population. That's okay. So now let's calculate our confidence interval. Okay, so our confidence interval is going to be equal to X bar for our sample, for our sample, plus or minus. Now, since I'm going to calculate the 95% confidence interval. Okay, it's going to be equal to X bar plus or minus. Anybody want to complete that for me? What's my multiplier going to be? My z-score going to be plus or minus z for alpha is equal to 0.05, right? Times our standard error. Okay, so if I'm going to complete this, what is X bar going to be? Thanks, I got Karen, that's correct, it's 1.96. So X bar is going to be our sample mean. Our sample mean is 648. Okay, plus or minus, okay, 1.96 as Karen has pointed out, times, because the z-score, that's our 95%. That represents, that number standard errors represents 95%, capturing 95% of the possible values for the mean, for the actual population mean to the left and to the right of the mean that we found when we sampled it, times the standard error. Well, now I got to calculate standard error. So I'm going to go up here and I'm going to calculate standard error. We know the standard error is equal to the standard deviation, or sigma, depending on what we know, divided by the square root of the sample size. Okay, and in our case, the standard deviation of the sample was 60 divided by the square root of the sample size, which is 36, which is 6. So 60 over 6 is equal to 10. Everybody comfortable with that? Thank you, Karen. Everybody's comfortable with how we got that 10? So it's 1.96 times 10. Okay, so our 95% confidence interval is going to be equal to 648 plus or minus, and I'm going to round this to 2 just to make it easy. Okay, don't round it for 2 when you do it. Okay, and it's going to say that the confidence interval is going to be between 628 and 668. We're 95% confident that the true population mean for Hunter Psych majors SAT scores is between 628 and 668. We took a sample of 36 people. We asked them their SAT scores, 36 psych majors. We asked them their SAT scores. We got a value of 648 for the mean. But when we actually went back and calculated, when we actually went back and took a closer look, we realized that that's the mean for only those 36. We have no assurance that the population mean is exactly that. In fact, we based on how variable the results were for these students, in other words, the standard deviation of the sample was 60, based on that variability, our best guess is that we can be 95% sure that the true population mean is between 628 and 668 for first year psych majors at Hunter. Okay, so how different than that is from the first year average first year Hunter student? Well, the average for the population of first year Hunter students, the average SAT score is 620. Notice 620 is outside of this range. We would less than 5% of the time would we get if we took a sample of size 36, less than 5% of the time, would we expect to get that small a number? Or in other words, another way of looking at this, probably more accurate way of looking at this would be, it looks like it's likely that our population mean for psychology students, which we believe is between 628 and 668 with 95% confidence, is different than our known mean for SAT students, which is 620. We don't have to calculate a confidence interval for the rest of the population of Hunter students because we measured every one of them. We know what the mean is actually is. So we're going to test this again using the t-test momentarily. Okay, but before we do that, I want to look at the effect of changing the sample size here. So now what I'm going to do is I'm going to go back here. I'm going to copy this, and I'm going to paste it here. And I'm going to change this from a sample size of 36 to a sample size of 25. Okay, so let's see what the effect of this is going to be. It's going to have two effects on us right now. Okay, so first of all, now, do I know sigma? Okay, do I know sigma? I don't, do I? Right? That's still a no, right? Okay, that's a no. Do we have a large sample size? Okay, how do we feel about that? Do we have a large sample size? Yes, and Karen, let me address that in a second after I answer this. Yeah, no, we don't have a large sample size. We have a small sample size. It's less than 30 people, right? So now I can't use the z-test. I can't use the z-distribution to solve this, to create my confidence interval. Now I have to use the t-distribution. Okay, so let's go ahead and do that now using the t-distribution. First thing I'm going to do is calculate my standard error. We automatically now have a difference in our standard error because we have a smaller sample size, and standard error is based on the sample size. Now, standard error is going to be equal to our standard deviation for the sample, which is 60, because we have nothing else to base it on if we're not given sigma, divided by the square root of the sample size, which is 25, the square root of 25 is 5. So now sigma is equal to 12. So immediately we see a difference here. Our sigma is a larger number. That's going to contribute to the width, right? Smaller sample now, it's going to make things wider because we're going to multiply by, we're going to add and subtract a bigger number from our mean. Okay, so let's calculate our confidence interval. Okay, so when we calculate our confidence interval now, it's going to be x bar, which is going to be 648 again, plus or minus, right, plus or minus. Okay, now I have to come up with, instead of my z-score for 0.05, actually, I really should have called that, instead of 0.05, I really should have called that for alpha over, I should put alpha over 2 is equal to 0.025, or half of that 5%, because we don't know if our result was going to be higher or lower than the mean that we're comparing it to, the population that we're going to compare it to. So I'm not going to worry about that now. I'm just going to put our t-score, right, times our standard error. I don't want to get things too confused right now. Okay, so what's that going to be equal to? Okay, so it's going to be equal to 648, right, times, where am I going to get the t-score from? Anybody want to hazard a guess where I'm going to get this t-score that I need? Let me make sure you guys are all muted again. Whoops. There it is. I got my t-table. So my sample size is 25. So I go down here to 24 degrees of freedom, right? Degrees of freedom. 24 degrees of freedom. I go across here to, it looks like, I think it's the third row over. So our 95% confidence interval is based on a t-score. Now, when they say t is equal to 0.025, they're saying the right tail probability. In other words, we want to get far enough from the mean to say that there's only a 2.5% chance of getting a number further away from the mean. 2.5% on the top half, or since we don't know to start off with whether it's bigger or smaller, 2.5% below that number on our low end of our confidence interval. Okay, so 95% of possible outcomes are between those two numbers. So we're going to use this column here, the 95% confidence interval with a t-score of 2.5% on each tail. In other words, a probability of being wrong of 5%. We're going to go down here to 24, and we're going to see our t-value is 2.064 instead of 1.96. So this is 2.064 times our standard error, which is now 12. Okay, so what's happened here? This is going to make our confidence interval, since we're going to multiply a bigger number times our standard error, we're going to be adding and subtracting, plus or minus. We're going to be adding, plus or minus. We're going to be adding or subtracting a larger number from our sample mean to get our confidence interval. So now this is going to be spread out further. That's the effect of the t-distribution. It makes us make our confidence interval wider in order to have the same level of confidence that we've captured the true population mean. Okay, and that's making up for our less secure understanding or knowledge of what the population standard deviation is, because we had to depend on a small sample size. And the smaller the sample size, the bigger the t-value is going to be, right? So if I went back here and looked at these t-values again, as the sample size gets smaller, t gets larger and larger until with a really small sample size, it really gets quite large. Okay. So at any rate, let's calculate our confidence interval now. Whoops. Let me go back here. Let's calculate our confidence interval using the t distribution now. So I'm going to get my calculator up for this. So this is going to be let me do that. 2.064, okay, times 12 is equal to this. I'm going to put that into memory. I'm going to clear that. I'm going to say 648 minus, that value is 623. Okay, and I'm going to go back there and get to it again. Except this time, it's going to be 648 plus 24.76, which is 672. Okay, so now, in order to be 95% sure that we capture the true population mean for psychology majors, we now, instead of being 620, having a range from 628 to 668, we have a range from 623 to 672. Okay, it's gotten to be a wider range. And what's caused us to have that wider range? The fact that we had less confidence, so that we had to use the t-score and the z-score in our standard deviation, and also partly because the standard error is a larger number because we had that same effect from the smaller sample size. Okay, so that's the way that we would make a judgment as to what these were. So I want to do another example now. Actually, I'm going to go through these now for a t-test. We're going to take a look at if we encounter this same kind of situation for a t-test, what this might look like, and then I'm going to do proportions when we finish up. So let's do the same thing now, except we're going to look at it from the perspective of a t-test. And what is a t-test going to do? We're going to determine the number of standard deviations apart, actually standard deviations of the sample means, which is, we happen to call it standard error. Number of standard errors apart that the population mean and our sample mean are. Okay, how many standard errors apart are them? And we're going to say to ourselves, in order for us to reject the null hypothesis that the true population means for both of these are the same thing. In order to be able to reject that, we want these to be at least 2 standard errors apart. In other words, we want the z-score to be at least the z-score for the difference to be at least 1.96. And we want, if it's a small sample size, we want the t-score to be at least whatever that number has to be for the samples, for that particular sample size. In other words, we're going to call that the critical value. Okay, critical value for z is always 1.96 because that's what we need in order to have less than 5% chance that the means are the same. Okay, for t, that critical value, right, instead of being 1.96, for t, that critical value, it changes based on the sample size. So it's for each critical value is for a particular sample size. So how are we going to calculate that? We're going to calculate it by saying that the z-score, z or t, okay, is equal to, okay, what's it going to be equal to? It's going to be equal to our sample mean, x bar, minus our population mean that we're comparing it to, divided by the standard error. Okay, that'll give us how many standard errors apart that these two are. Okay, I'm going to start with our first example where we either knew the population standard deviation or the sample size was bigger than 30. So we assumed that we knew it because it was 60, the same as the sample, our sample. Okay, so let's take a look at doing this. Okay, so I'm going to go back up here to where we did our calculation for our confidence interval. I'm going to say this time I'm going to do a single sample t-test. Well, the first thing that I'm going to do before I do a single sample t-test is I'm going to set up a null and alternative hypothesis, H null and H alt. Okay, anybody want to propose a reasonable null hypothesis for me? That's correct. If z is greater than 1.96, z is greater than 1.96, we can reject the null hypothesis. If it's less than 1.96, the two means are too close together to say for sure that the population means are different. The sample mean is too close to the other mean to say that it's different. We want them further apart. Okay, and we're going to see that in just a second. Anybody want to propose a reasonable a null hypothesis for me? No difference between the sample and the population mean. I like that. Okay, except that really, we're never comparing, when we do it on null hypothesis, we're never stating as if we're working with samples. Okay, we want to prove that the population mean, mu, for psych majors is equal, well, we're going to start with the assumption mu for psych majors is equal to mu for other students. Okay, we always state it for the population, even though we are forced to use a sample mean because we don't have the population mean. We're starting. Our real assumption is that the two population means are the same to begin with. So that means our alternative hypothesis is going to be that they're not equal. Okay, and I'm going to show that over here on my typewriter by doing it this way. Are not equal. The two means are not equal. So now I have to prove, in order to reject my null hypothesis and prove my point that psych majors are smarter than all the other students at Hunter, right? If that was what my point was. In order to prove that, I have to reject the null hypothesis. That's my objective, and accept the alternative hypothesis. In other words, the deal here is that I'm unwilling to say that I've proved my point unless I can, with a lot of confidence, 95% confidence, with less than 5% chance of being wrong, reject my null hypothesis that they're the same before I accept the alternative. Okay, so let's go ahead and give that a try for this particular example. So our z-score is going to be equal to, let's see, the mean for the sample is 648, x bar minus mu, mu is 620, divided by the standard error. The standard error that we calculated before was equal to 10 for the sample size of 36, divided by 10, So that's going to be equal to 28 divided by 10, or 2.8. Okay, everybody comfortable with that? So can I reject my null hypothesis? Anybody want to hazard a guess? Can I reject my null hypothesis? My z-squared, my number standard errors apart. That, yeah, I agree with you. I can reject my null hypothesis and accept my alternative hypothesis. Okay. Now, had this come out to 1.7, could I reject my null hypothesis then? No, I couldn't, because I didn't exceed the z-squared. They're not far enough apart for me to say with 95% certainty, less than alpha error, less than 5%, right? It has to be more than 1.96. I'm going to ask you one more thing. Can I say, okay, I can't reject my null hypothesis. Can I say I accept my null hypothesis? No, you can't, right? Because you didn't prove anything. All you can say is, I fail to reject my null hypothesis. You didn't prove this is true, right? You didn't prove that the mean for psych majors is equal to the mean for others. All you did was fail to get the evidence you needed to say that this was not true so that you could accept your alternative, right? So you can't say that you accept your null hypothesis. You can just say you failed to reject it. Okay, if you were able to reject it, in this case where it was 2.8, the number we actually got, in that case I could say I reject my null hypothesis and I accept my alternative hypothesis.